Good morning, everyone. Now I am giving seminar probabilistic theory and Socratic process. My role I am from ECA section. My roll number is 24 BQ1A0401. I'm explaining about the topic random process. A random process is a collection of random variables that change with time. And this have another name stochastic process. In simple terms, it is a time varying random signal. These have some example message signals in communication, background noise in a receiver, variations in weather like temperature and rainfall, speech or music signals. And these have simple definition. We not like that. We have some simple definition. A random process is a collection of random variables indexed by time or space. It tells how a quantity changes randomly as time progresses. These have not in the slide examples. These have some more applications and examples. Thermal noise in an electrical circuit is also one of the example. The voltage changes randomly over time. And stock prices. Stock price varies unpredictably. This is also an example of random process. Number of phone calls arriving per minute. Random count over time is also considered as a random process. And next, why do we use random process? We use random process to study signals that change unpredictably with time, such as noise or message signals. We cannot fully know their behavior, only their statistical properties like average, power, variance, etc. can be known. Hence, they are described statically, not deterministically. They help to model real world phenomena where outcomes cannot be predicted exactly but can be described statically, such as communication system, signal processing, economics, weather forecasting, etc. We use random processing because many real world signals and behave uncertainly and cannot be predicted exactly. But they can be described using probability. Random process gives us a mathematical way to analyze, model, and predict such uncertain behavior. Reasons why we use random processes. Real world signals are unpredictable. Example, if the signal have a noise in communication, we can't predict the noise. Wind speed, traffic flow, stock market prices. This cannot be expressed by a simple formula. A random process helps describe them using probability. To analyze noise in electronic and communication system, easy communication channel has noise that varies randomly. To design receivers, filters, and modulation schemes, you must understand how noise behaves, how it affects signals. Random process theory allow precise analysis to noise. To make reliable predictions, even though we cannot know exact future values, a random process allows us to predict average behavior, variability, correlation. To design systems that work under uncertainty. Engineers design system assuming random inputs, radar systems, communication networks, control system, random process give a framework for designing optimal and robust systems. To model real life random events, uh, number of calls arriving at a call center, packets arriving in a network, rainfall distribution, heart rate variations. In simple words, we use random process because the world is uncertain and we need a mathematical tool to understand, analyze, and design systems that work under this certainty. So we use it. After that, we have statistical description. Because the exact values at every moment are unknown, we describe the process using statistical measures such as probability distribution function. PDF gives the probability of different values. Probability density function describe how these probabilities are distributed. We have difference between probability distribution function and probability density function. Probability distribution function, just now we see that probability gives the probability of different values, but probability density function describes how these probabilities are distributed, and probability distribution function is denoted by capital PDF and probability density function is denoted by small PDF. These functions tells us everything about the random statistical behavior of this signal. And the next one is energy and correlation. Random processes have infinite energy because then they exist over all time. So instead of total energy, we study finite energy functions like correlation and covariance function. Now we see correlation function. Correlation function measure how similar the signal is to itself at different times. Covariance function measures how two random signals vary together. This help us to understand the time domain behavior of random process. And the next one is examples. These have so many examples. One these have so many examples. One is that common example of random speech and music, background music, and changes in weather, variations of received signals in communication. Uh, and the next slide is about random process. Random process is a time-varying random phenomena described statically using tools like PDF. Small capital PDF means probability distribution function, and small PDF means uh, probability density function, correlation, covariance, which help us understand and model signals such as noise and message signals in communication system. And the next one is random process have a temporal characteristics. Definition: a random process or stochastic process is a process in which a random variable depends on both. It depends on both time and sample. Time is denoted with t and sample space is denoted with small s. Time means how the variable changes over time. Sample space means the random outcomes from an experiment. So a random process is written as x of s comma t. S means we have already seen that s means sample space, t is time average, or simply x of t. S represents the randomness in the signal and t represents the time average. Next slide is when the sample space is S. When the sample space is S is fixed, you are looking at one particular outcome. It becomes a real function of t, represented as x of S1 comma t. Means S1 is varying and S1 is fixed and time is varying. This means for no one specific experiment S1, how the signal changes over time. Example, the waveform of one realization of a random signal, like one recording. And the next one is when both time t and sample spaces are fixed, both are given specific values, so it becomes a constant represented as x of s1 comma t1. Example, the value of a signal at a specific instant in one experiment. In this, both time and sample space s are fixed. Now we see the conditions, representation, nature, example. If time is variable, sample space also variable, we represent it as x of s comma t. Its nature is random process. Example, random signal. We completed this first one, and after the next one is time fixed. X of s comma t1. T1 means time is fixed. S is not, S doesn't have any suffix numerical, so it is variable. Uh, this nature is random variable, and this have example, that is noise at a particular instant. Sample fixed. If sample is, we already see that if which have fixed one thing that have in suffix numerical, which does not have fixed, that doesn't have any numericals in their suffix. So in this, sample is fixed. So x of s1 comma t. Nature is time function. And this has example is one noise waveform. If uh, both are fixed, means time sample both are fixed. So we write x variable capital X of s1 because s is also variable, s is also fixed, t1 is also fixed. So in their suffix we write 1. So x of s1 comma t1, nature will be constant, and example is single value of random process. And this is all about the random process. In this we see condition, representation, nature. Example, for random process, for time variable, sample space variable, we see random signal. For time fixed, we see noise at a particular instant. For samples fixed, we see one noise waveform. For both fixed, we see signal value. Okay, thank you.